Andrei Mihelic from Jovan Stefan Institute of Ljubljana. Yes. Is going to speak about multi-photon ionization of few electron systems, amplitudes, and cross-sections. So please, Andrei.
Okay, thank you. So let me share my screen.
Yes.
And so is everything okay?
Yes, I can see it. Perfect.
All right.
Thank you.
So thank you. So I'm going to talk about the calculation of multi-photon ionization amplitudes and cross-sections. Or more specifically, I'm going to present a method that we have devised for this purpose. So let me first say that this method has been developed in passing, so it is a sort of a byproduct that we managed to develop and is actually connected to our activities in this field. So the method itself is actually based on the time-independent perturbation theory and exterior complex scaling. But we nevertheless thought that it is interesting enough to be presented on its own here. And this is what I'm going to do. So first I'm going to try to explain how the method works, what it is based on, and then I will show you some results that were obtained by this method. So in order to do this, let us first review how to calculate single photon ionization amplitudes. So we start from an expression like this, where psi0 is an initial bound state with energy E0, D is the dipole operator, and psi f is the final state of appropriate asymptotic, which contains all final state interactions. Now, that kind of amplitude can be obtained if one looks for a solution of a driven Schrödinger equation, which satisfies the outgoing boundary conditions. So in this equation, H is the total atomic or molecular Hamiltonian, and E is the final state energy, which is written here. And of course, psi hat is the outgoing wave solution of this equation. Now, the photofragmentation process is usually described in terms of channels or channel wave functions. And these channel wave functions are usually the eigen wave functions of the channel Hamiltonian, which can be, in fact, different from the total Hamiltonian. So in our case, we will assume that this channel Hamiltonian includes all the long-range interactions, and the rest, so the short-range interactions, are included in this term VF. And furthermore, we will also assume that the volume we use to describe our wave functions is big enough so that that the effect of this short-range potential dies out once we approach the boundary of this volume V. Now, if this is the case, the photoionization amplitude can be written in a form of a surface integral. And this integration actually runs over the boundary of this volume. And this particular form is very convenient for the calculation of the amplitudes, because it contains no explicit potential, for example. It only contains the channel wave functions and the solutions of the driven equation. In practical calculations, that kind of an integral actually simplifies to Wronskian, where the let's say radial function of the channel wave function is used, and the radial function of the of this solution of the driven equation, and both of them are evaluated at a single radial point which lies inside this volume V. Now, in order to solve the driven Schrödinger equation, which in order to impose the correct boundary conditions, we can use the method of exterior complex scaling, which is based on a complex transformation of coordinates outside of radius R0, which is called the scaling radius. And this is what we have done here for the case of the hydrogen atom. So plotted here is the, let's say, radial function of this solution psi hat for a specific channel. Okay, and as we can see, this wave function reaches asymptotic behavior inside this non-scaled region of space. And this means that it can actually be written in this asymptotic region in a form of an outgoing Coulomb wave. The Wronskian I mentioned earlier, so the amplitude actually consists of this p hat, so the radial function of psi hat, and of the regular Coulomb function, the normal one, so of the hydrogen atom. So this actually holds for the hydrogen atom, but it turns out that the same kind of approach can also be used for heavier atoms or molecules, provided that the point at which we extract the amplitude lies far away from the origin. Okay. Now, is there a way to generalize this approach to two or more photons? So one would think that that kind of approach should be easily extensible, so generalized to let's say 2 photon absorption. So we just complement the equation we have used, so the driven equation for the first order solution with an additional step. So we calculate the second order solution by using the first order solution as the driving term for this second equation. And in the same way as before, we can calculate the 2 photon ionization amplitudes by analyzing the second order solution in terms of channel functions again. Well, the problem with this approach is that it works as long as the energy in the first step lies below the ionization threshold. And the reason for this is that as soon as we reach above the threshold, the extent of this solution becomes infinite. So we cannot actually enclose the driving term in a finite volume, which breaks one of our assumptions that we made. Now, this problem has actually been addressed by using a complex photon energy, and then by extrapolating the results to let's say to zero value of this imaginary constant, which makes actually the driving term exponentially damped, and this makes the let's say the solution of the so the second order solution well behaved in this case. Now this introduces some other problems. In most of the cases it works very well, but as soon as you hit, for example, intermediate resonance state, this kind of an extrapolation causes artificial broadening. And here we will try to explain how to avoid this. So we will I will give you an alternative way of calculating these two and multiphoton amplitudes. So let me start by saying that we will concentrate on the velocity form of the dipole operator from now on, and the reason for this will become clear soon. Here below, I have calculated the let's say I have plotted the radial function of this second order solution, again for one specific channel. And a quick glance at this this form actually doesn't reveal any useful information. Okay, but this is just the first glance, because if we plot the real and imaginary parts of this radial function separately, the pattern we see here looks awfully like a beating. So this bit-like pattern can actually be described by a superposition of two Coulomb waves with fixed wave numbers. And even more, those fixed wave numbers are actually exactly equal to the wave numbers K1 and K2, which correspond exactly to the energies of the first and the second step. So it is actually very very easy to write the form of this, and we know what the wave numbers are actually. Now, in heavier atoms or molecules, the relation between the energy and the wave number is not so simple anymore because of the energy of the core or the ionization potential. But the general idea still stands. So what one gets from the calculation is something very similar. Okay. So now, what is the actual reason that we have, let's say, two wave numbers present in second order solution that we obtained? Well, this becomes clear if we look at the let's say two photon ionization in hydrogen. So we start from 1s, and if we are about the threshold, we proceed through some continuum state, and by absorbing another photon, we end up in a higher lying continuum state. And this second part, second step of this two photon absorption path, is actually described by the dipole matrix element, the continuum matrix element, which has this kind of form. Now, if K1 and K2 were actually plane waves, it would be clear immediately that that kind of dipole matrix element is actually proportional to the delta function in K-space. So it is different from zero only when K1 and K2 are equal. A similar relation also holds for Coulomb waves. It is not exact, it is approximate, but it holds pretty well. And this is sometimes referred to as on-shell approximation. It has been used under different names. And this is actually a pretty good explanation of what happens. So in addition to the expected wave number we have, this is the wave number associated with the energy in the final step, there is the intermediate step wave number also somehow imprinted onto the second order solution. And the reason is somehow this relation. Now, in heavier atoms, for example, several channels can be open in the intermediate step. And this means that several different wave numbers can be imprinted onto the final state solution, so the second order solution. And this is why we can guess what an appropriate ansatz for the asymptotic form of this radial function. So it consists of a sum of weighted Coulomb waves. Actually, it consists of several Coulomb waves with fixed wave numbers, and all of those wave numbers can actually be calculated in advance. And this two-photon approach can actually be generalized to many absorbed photons. And in the case of multi-photon absorption, actually all of the previous wave numbers get imprinted onto the let's say solution of the final step. And now all we need to do to calculate the photoionization amplitude in the case of two or multi-photon ionization is that we calculate the amplitude which corresponds to the last, so to the final step, so to the wave number, let's say Kn, if there are n of them. And this is actually much simpler than it looks. So if this can be done in the following way. So if we have, let's say, this asymptotic form of the radial function, all we need to do is let's say, calculate the Wronskian of the left-hand side and the right-hand side of this approximate equation in at several points, all of which lie inside this volume and actually lie inside the non-scaled region of space. The only condition is that they must be from the part of space where the asymptotic form of this function is already valid. Okay. Now this problem can be cast as a minimization problem, and this of course can be solved by solving a normal system. And this normal system is solved by a simple pseudo-inverse, so with singular value decomposition of this matrix and diagram. This is actually much simpler than it looks, and it is very efficient and very stable. And as far as we were able to test, it gives very good results. So, and the results is what I show next. So here I show you the multi-photon ionization cross sections. In fact, 2, 3, and 4 photon ionization cross sections for the hydrogen atom. These cross sections have been compared to the known results, actually to the analytic values calculated by Karole. And as you can see, there is excellent agreement both below and above the ionization threshold in all three cases. So for 2, 3, and 4 photon cross section. All the features you can see are actually reproduced without any problems, so without any numerical difficulties. Now, we have done a similar thing for helium. So we have also tested this with helium and compared this to existing results. So here I show you the 2, 3, and 4 photon ionization cross sections. Here the results below the ionization threshold, which I think agree with the results of Alejandro and Peter Lambropoulos rather well. We also checked the results above the ionization threshold, and it seems that, it turned out that that it agrees with the results that we could find in the literature rather well. So we could reproduce, for example, the resonance, cross sections, and also the so-called core excited resonance states. So I didn't mention this when I talked about the method, but it is also possible to have transitions in the continuum in which, let's say, the excitation occurs in the atomic core, and the continuum electron acts as a spectator. And this results in a very strong enhancement in the cross-section, and this has been named a core-excited resonance state. Okay, so it is actually very interesting to compare the results of the time-independent calculation to the cross-sections that have been extracted from time-dependent wave packet. We have actually used the method that has been developed by Alicia Palacios. Alicia was also kind enough to help us with the implementation of this method. The method itself looks actually very, very similar to what we have used. So you have to calculate the inverse of a driven time-independent Schrödinger equation, but with the driving term, which is replaced by the wave function at the end of the pulse. Okay, and what we obtained are the black dots here, which agree very well with the perturbative results. The only differences that can be seen here stem from the let's say spectral broadening, which are the consequence of the finite duration of the pulse. In this case, we used a pulse of 80 atomic units, which is approximately 2 femtoseconds. And now I show you the last slide of the results. So we also calculated the asymmetry parameters for 2, 3, and 4 photon ionization of helium. So these asymmetry parameters, or beta parameters, are used to characterize the photoelectron angular distributions. This has been done, of course, again in helium for 2, 3, and 4 photon ionization. And we have compared this to recently obtained results by Diego Boll. So here you see the points which practically coincide with our results. And again, there are some differences, but those differences can be easily attributed to the broadening which comes in because of the finite pulse duration, because the values that were extracted in this article were extracted actually from the wave packet. With this slide, I will conclude, and I will also invite you to comment or to ask questions if something was unclear. Thank you very much.
Okay, thank you, Andrei. Thank you for the nice presentation. So we have some time for questions and comments. You know that for your questions, you can use the participant list. So please raise your hand. I don't see any question. So, Andrei, in the meantime, I have something to ask you.
Yes.
In general, for larger systems, does this approach take into account correlation for any states, so initial, intermediate, final states?
Yes, as a matter of fact, this takes all the interactions into account. I mean, the electron-electron interactions fully. So it's basically a complete approach.
Okay.
And we have actually tested this. So the initial tests were done with the close coupling basis.
Mm-hmm.
So we are pretty confident that it can be used for larger systems. It can be probably used in simple molecules as well without problems.
Mm-hmm. Okay.
So, and probably it's more efficient if close coupling basis is used, because we used a basis of B-splines to describe both electrons.
Okay, thank you.
Thank you.
I don't see any further questions, so thanks again to Andrei, and let's move on with the next speaker, who is, the next speaker is Sandor Borbeli from Babes-Bolyai University, Cluj. Are you there, Sandor?
Yes, I'm here. Can you see my...
Okay, yes, I can see your...
full screen is working?
Perfect, yes, it's working, and Sandor is going to speak about wave function splitting technique used for the study of interference effects. So please, Sandor.
Okay, thank you for the introduction. As you have already heard, I will speak about the wave function splitting technique, which can be used to study interference effects. And we use this wave function splitting technique in the context of photoelectron holography. I will start my presentation with a short introduction in which I will explain in more detail what I understand under the term of photoelectron holography. After that, I will show you very briefly the methods which we used during our calculations. And after that, I will talk about the physics behind the photoelectron hologram formation. And the last topic I will touch will be the influence of the target atoms on the obtained photoelectron hologram. As you all know, when you have an atomic system which interacts with a few cycle laser pulse, as a result of this interaction, continuum electrons and high harmonic photons are produced, which can be detected, and these detected particles can be used to extract some structural information regarding the target atom or molecule. One of these methods is a well-known attosecond tomography, which uses the high harmonic generation spectrum. Another technique is the laser-induced electron diffraction, which uses the spectrum of the continuum electrons. And a recent method is a so-called photoelectron holography, which also uses the continuum electrons. The photoelectron hologram or holography is strongly connected to the intercycle wave packet interference effects. Basically, if you want to see wave packet interference, you need at least two distinct wave packets which can be coherently added in the detector, and which may lead to some very interesting interference effects. In a context of an external laser field, you can define several interference scenarios depending on the relative birth time of the two interfering wave packets. So if both of your continuum wave packets are created during the same water cycle of the driving laser field, then during the laser-driven dynamics of these wave packets, there will be some trajectories which will be strongly scattered by the parent ion, and there will be trajectories which will be less less strong, only weakly scattered by the target ion. And in the continuum, these two trajectories may interfere, and this interference leads to this very nice interference pattern, which in the literature is called also called the spider-like hologram. This interference scenario is also is called as a spatial interference because it's the root of this interference is can be found in the interference between different spatial electron trajectories. The other interference scenarios can be called as temporal interference because the interfering wave packets are created during different time moments. And if you have the two wave packets created in two consecutive quarter cycles of the driving field, the resulting interference pattern looks like this. If the second wave packet is created at the third quarter cycle of the driving field, and the resulting interference pattern looks like this. And if the second wave packet is created at the fourth quarter cycle of the driving field, then the interference looks like this. If you take a look at this schematic picture of these interference scenarios, then you see that in all cases, you will have an interference between strongly scattered and weakly or not scattered wave packets. So this can be interpreted as a holography, since the strongly scattered wave packet can be considered as the signal wave, while the weakly scattered or not scattered wave packet can be considered as a signal wave. Okay, the photoelectron holography was first experimentally observed 10 years ago by Imke Huntsman and co-workers. As a target, they have used metastable xenon atom as a target, and in the measured photoelectron distribution, they have observed a very nice interference pattern, which is very similar to this spider-like structure or spatial interference effects. And in the last few years, we spent quite a lot of time to investigate this kind of interference effects, namely this spider-like photoelectron holography. This spider-like holographic pattern can be understood in the framework of a very simple so-called two-path models. You assume that under the action of your external laser field, a continuum electronic wave packet is created at the Z0 distance from the core. And in this electron wave packet, you will have electron trajectories which are weakly scattered, and you have strongly scattered electron trajectories. And if you calculate the phase difference between these two trajectories, the interference pattern can be described with this very simple analytical formula. And if you plot this interference pattern, then you see it's very similar to the interference pattern which you can obtain using ab initio calculations, namely the numerical solution of the Schrödinger equation. And this very simplistic model can be used to understand how the laser field parameters are influencing the shape of this interference pattern. But here I won't talk too much about this because I have other subject. In order to study these interference effects, we have used two-cycle laser pulse. It's a time-symmetric laser pulse. We choose this laser pulse shape in order to have the spatial interference as a dominant interference effect in the momentum distribution of our continuum electrons. And our main goal was to study the wave bucket in the dynamics and to identify and understand the ongoing processes. And as a tool, we have used the numerical solution of the time-dependent Schrödinger equation for single active electron systems. Our approach is pretty standard. For the angular part of the wave function, we have used the spherical harmonics as basis. The radial part of the wave function is discretized on a finite element discrete variable representation grid, which basically it's very simple. You have the configuration space which you split into finite elements, and inside each finite element you represent your wave function using a polynomial basis. This approach is very flexible because you can adjust your grid density as requested by your problem. And for time propagation, we have used the Arnold-Lantzos method, which is very convenient because it's stable regardless of the time step size, and you can implement very easily an automatic time step control. During our simulation, we need an initial state. In simple systems, as in case of the hydrogen atom, it's known analytically. In more complex systems, we just diagonalize the field-free Hamiltonian, or we just perform a negative imaginary time propagation. And as a result of our TDSC simulation, we obtained the time-dependent wave function from which the ionization probability densities are extracted by projecting these wave functions onto exact scattering state. Just to illustrate what's happening when you have a few cycle laser pulse interacting with a hydrogen atom, I will show you a very short animation. You will see here in this panel the momentum distribution of the continuum electrons. In the right panel, the momentum distribution of electrons, the coordinate space distribution of the electrons. Here you will see you have the shape of the laser pulse. By here with a vertical red line, we have indicated the actual time during the simulation, and the last figure shows the total ionization probability as a function of time. And as you start the simulation at low and moderate intensities, you see a very nice dipole-like photoelectron distribution. But as you increase your field intensity, you arrive to the tunneling and over the barrier ionization, where you will create a very large unidirectional and compact electronic wave packet, which departs from the core. You can see this here in this plot. And with propagating this system further with the change of the electric fields direction, this very broad continuum electronic wave packet is returned to the core, where it is scattered, leading to this very nice interference pattern. You can continue the propagation. Further electron production, continuum wave packet production occurs, and more rescattering events. And after the quiver motion of this electronic wave packets, you will arrive to the final distribution of your electrons, either in momentum space, either in coordinate space. With the ab initio simulation, it's very nice that you get very high precision results, but the main drawback of this ab initio simulation is that it's very hard to extract from a final state more information regarding the physics of the processes which led to this final momentum distribution of the photoelectrons. So in order to get more information out of our TDSC simulation, we have implemented a wave function splitting technique. which is a very simple approach. Basically, in the time axis, we have defined some checkpoints. The checkpoints are those points where the strength of the electric field is 0. And we have started our simulation from the initial state, and we propagated our system until the first checkpoint. At this checkpoint, we splitted our wave function into 2 parts. The first part contained the bound wave packet, and the second part, the C1 part, contained the continuum part of the wave function. But now, to this C1 wave packet, we can assign some physics, because we know that this C1 continuum wave packet was created between the starting point and the first checkpoint. So basically, this C1 wave function contains the continuum electron wave packet created during this first peak of our driving field. Now, after we had done this wave function splitting, we propagated these 2 wave packets separately, the bound wave packet and also the C-bound wave packet, until the next checkpoint. And at this checkpoint also, we have splitted each of our wave packet into 2 parts, the bound part and the continuum part. So basically, when we splitted the C1 wave packet at T2 time moment, we obtained some bound partial wave packet, which describes the electrons which were recaptured during this second peak of the driving field. We do not want to follow them further, so we put it back into the bound wave packet. And in the bound wave packet, after the splitting, we have obtained the bound part and the continuum part, which we have noted with C2. And this C2 wave packet contains the electronic wave packet, which was created during the second peak of our driving laser field. And we have continued this procedure until the end of the laser pass, where we ended up with 1 bound wave packet and several continuum wave packets, but to each wave packet we could assign a birth time, an approximative birth time. Basically, we know that the C1 wave packet was created during the first peak, the C2 during the second peak, and so on. And we have applied this wave packet splitting technique to a model helium system. Basically, after we have obtained this partial wave packet, we have calculated the momentum distribution of the continuum electrons which for each wave packet, and you have here the C1, C2, C4 and C5 wave packets. The first one and the last 2 wave packets are low in intensity, so they are not so relevant. The main physics is hidden in these 2 wave packets. And if you take a closer look at this C3 wave packet, you can very nicely identify that is basically it's a very simple spider-like interference pattern, which is the result of the spatial interference. And basically, sorry, I wanted to go in the other direction. The C3 wave packet was created during this peak of the laser field, and during the next peak of the laser field, it was scattered by the target ion. So basically, this third wave packet is very nicely structured because it suffered only 1 scattering by the parent ion. The second wave packet is not so nice because it suffered multiple, namely 2 scattering by the core, so it has a more complex structure. Now, with these techniques, we can very nicely see how this temporal interference pattern is formed. spatial interference pattern is 4. Now, in the next step, if you start to add up coherently these partial wave packets and you calculate the resulting momentum distribution of the some wave packet, you will see showing up the temporal interference patterns, which are as root as the interference between wave packets created during different time moments. So if you see here, by adding up the first two wave packets, the result is as the same as the second wave packet, because the first one is a very weak wave packet. But if you add up the second and the third wave packet, the resulting interference pattern is very close to the final one. And in this pattern, you can identify that the outer region of the total momentum distribution is coming from the third wave packet, while the inner region is dominated by the second wave packet. And you see here a transition region between these two parts of the momentum distribution with some interference fringes. These interference fringes are rooted in the interference between the second and the third wave packet. Okay. By using this technique, we wanted to see how the atomic species of the target is influencing the resulting photoelectron hologram. So we have performed single active electron calculations for hydrogen and some noble gas targets using this model potential, and the results are here. And you clearly see that there is a significant difference between the different interference patterns. And if you compare the hydrogen with the argon, they are similar in structure. The same goes for the helium and neon targets. In the helium and neon, you see very clearly you have the inner region and the outer region. And the similarity between the hydrogen and argon and helium and neon can be traced back to the fact that the ionization potential for the hydrogen and argon is very close. The same goes for helium and neon. And due to these similar ionization potentials, when these atoms are interacting with our field cycle laser pulse, the created wave packet dynamics is very similar in the case of the hydrogen and argon, and also for the helium and neon. So if the similarity between hydrogen and argon can be traced back to this similar ionization potential, now we wanted to see the difference between hydrogen and argon. And to get a more detailed look, we have plotted the angular distribution for a fixed electron photoelectron momentum value here for hydrogen and argon. And you see that there are significant differences between the location of the interference minima. Namely, in the case of argon, the density of the interference pattern is larger. Basically, the spacing between the interference minima is smaller compared to the hydrogen target. And this difference can be traced back to the fact that in the case of the argon atom, the returning electron, the strongly scattered electron trajectory meets with a much deeper ionization potential in the case of argon. So along this trajectory, the electron is accumulated much more phase, which translates to a larger phase variation as a function of the electron ejection angle. The same can be observed also in the case of the helium and neon pairs, but in this case, the difference is not that much. And another question related to this photoelectron holography we wanted to ask is to see how the angular symmetry of the initial state is influencing the interference pattern. And in order to investigate this, we have performed calculation for a hydrogen-like target, where as initial state, we have used the 2s and the 2p initial states. And we've performed the TDSF calculations, and you see here the final result of these calculations. And you see that there are significant differences between these two photoelectron momentum distributions. However, if you take a closer look and you plot the angular distribution of the photoelectrons for a fixed electron momentum, you see that the location of the interference minima in both cases, for both initial states is at the same place. So from this, we can conclude that this interference pattern, namely the location of the interference minima, is not influenced strongly by the initial state's angular symmetry. Now I will arrive to the end of my talk. We can say that we have a very good understanding how the photoelectron hologram is formed. We know how the laser field is influencing the density of the interference pattern. We showed that the photoelectron hologram is target sensitive and is not influenced too much by the initial state's angular symmetry. And but in order to have a very nice technique and a useful technique, there are some open questions which should be answered. The main question is how to extract structural information from the photoelectron hologram. So this technique can be useful only if you measure a photoelectron hologram, and from that you can reconstruct the scattering potential. And also another interesting question to answer is how this photoelectron hologram is influenced by the electron-electron correlation effects. And before I finish, I would like to thank my colleagues because this work was done in collaboration with Ladislav Nagy and Attila Tóth. And I conclude by thanking you for your attention.
Thank you, Sandor, for the nice presentation. Now we have a few minutes for the questions. So let me see. Yes, I can see a raised hand. Carl, please. You are okay.
Yes, perfect. Hello, thank you. Thank you for this very nice talk and very, very fancy animations. I really like that. I have, maybe it's a naive or stupid question, but so in the beginning of the introduction, you showed experiments, if I'm correct, they are in the IER regime, and then you were also talking on this animation slide. I think you said this part of the wave packet is created at its tunnel exit, but
yes,
on slide 9 you had an XUV pulse. So which I kind of missed the point.
Okay. Let me clear this. The experiment was done using IR pulses, but as you know, to do numerical calculations in the IR region, photon energy region, it's very time-consuming and resource-consuming because you have a very large wave packet quiver motion, so you need a large simulation box. And in order to study the physics behind this interference pattern, we choose a very short laser pulse. And in order to have a very nice pronounced interference pattern, you need a large amplitude to have a large quiver amplitude to allow the wave packet to form these two distinct electron trajectories, the scattered and direct one. So this is the reason why we choose these laser field parameters in order to avoid doing too large, too time-consuming numerical calculations.
Mm-hmm. I'm just wondering, if I go into the XUV regime, how well is the idea of a tunnel exit? Isn't this pulse long enough to completely completely deplete one side of your dress Coulomb potential? Do you really have a tunnel exit?
Basically, you don't need this tunneling ionization and over the bar ionization to have photoelectron holography. Basically, you need somehow to create a continuum electron wave packet which has a quiver motion, and it basically in the three-step model. In order to have this holographic pattern after the scattering, you need a decent quiver amplitude, and also quite a broad wave packet in the momentum space in order to have support for these interference patterns.
Okay, thank you. I would have a second short question, but I think Hakon has a question, so I would.
Okay. I think you can, yes, go ahead, because we have enough time. So,
okay,
yeah.
just a short question. How more detailed when you look at these at your spider interferences? How do you extract them? So is this what you are measuring in the vicinity of the Coulomb potential, where you just project some of the bound states out, or is it what you actually measure in your detector, like in your absorber, in the Coulomb-free case space?
Sorry, could you repeat your question? I didn't get the point.
Like these spider patterns you're showing, where you have the parallel and perpendicular momentum. How do you extract them numerically? Is this what experimentalists would measure in a continuum?
Yes,
like
yes.
What runs in the absorber? So it's not still the Coulomb potential underlying. This is like what will run into the continuum.
No, basically, you are asking that you see here, for example, in this C3 wave packet, this very nice spider-like structure, you cannot measure experimentally this. But you can measure the full momentum distribution, and this would be what they could measure in the experiment.
Yes. No, I mean, how you extract these pictures? Is this your wave function while the density is still at the nuclei core, or already when the whole density has moved out, basically?
No, basically, I have a time-dependent wave function. I do the time propagation. And after the end of my time propagation, I project my wave function onto exact scattering states.
Okay.
So in one-dimensional systems, you can numerically obtain these scattering states numerically.
Okay. Well,
so my answer would be that this is what the experimentalist would measure.
Okay, thank you.
Okay, Sandor, there is another question. Please, Hakon.
Yes. Yeah, also from my side, thank you for this very illuminating talk. I wanted to ask whether you are using, or I have maybe missed it in the presentation, if you're using any absorbing techniques. So, because you said you need large boxes when you want to go to the infrared regime, which would be closer to the experimental data. And therefore, I can only figure that reflection problems will be very strong and very strongly visible in such wave functions or such interference patterns in the end.
Yes, so. In our radio grid, at the end of the radio grid, we have an absorber, but we use that only just to see if the wave packet reaches the end of our simulation box.
I see. Okay, I'm just asking because with infinite range exterior complex scaling, there is, of course, a quite useful or quite effective absorbing technique available, yes. which would make it possible to propagate with tremendously less efforts and tremendously smaller boxes.
That should be implemented also in our code. It's on our radar. We know about this possibility, but we need time to implement it.
Okay, all right, thank you.
Thank you.
Okay, thanks again to Sandor, and let's move on with the next speaker. The last speaker of this session is Patryk Jasik from Gdansk, sorry for the pronunciation, University of Technology, and he's going to speak about quantum dynamics in systems with weak and strong coupling, the special case of diatomic silver anion. Please, Patryk.
Okay, thank you. Let me share my screen. Okay. Do you hear me?
Yes, we can.
Okay. What about?
You can share your screen in.
Yeah. What about my presentation?
Yes. Okay. Perfect.
Yeah. Okay. Thank you. So thank you very much for the invitation. It is a pleasure to be part of the Attochem community. Today I will tell you our story about silver, but I will talk more about weak couplings and a little bit less about strong couplings. This is our team from Gdańsk University of Technology, which created results which I will show you. And here is also Dariusz Kędziera from Nicolaus Copernicus University, who was responsible for optimization of the basis set and creation of potentials. But I will tell you about this later. Okay, our motivation is connected with a very nice recent experiment which was done by cryogenic double electrostatic ion ring experiment in Stockholm. And in this experiment, for the first time, it was possible to see the spontaneous emission from molecular anion dimer, which was a little bit surprised because in this system there is no crossing between ground states of the anion dimer and neutral dimer. And any avoided crossing. So the Born-Oppenheimer, so the non-adiabatic coupling is really small. But anyway, it was possible to see this in experiment, and the case was millisecond and seconds. So we will show you that it was we investigate this by theoretical methods. You can see here distribution of J and V numbers for which we can observe some two paths of decays. So one is electron emission only, and another one is fragmentation only. And here is only very small region in which the both decays are possible. And today I will talk about exactly about spontaneous electron emission. The scale is far away from atto-seconds. It is milliseconds and seconds because of weak couplings. Next, I will talk about rovibrational predissociation, which was the another path in this another path reaction in this experiment, and the time scale is picoseconds and nanoseconds. And we are working on methods which allow us investigate the dynamics in system with strong couplings. You can see here that vibrational levels of neutral molecule is in the soup of many vibrational levels of Ag2-. So if we couple this, we will be able to show the dynamics in very small scale. Okay, let me introduce our method, which allow us to calculate vibrational and electronic structure of anion dimer and neutral silver dimer. So it is a rather standard method. We have to solve time-independent electronic Schrödinger equation with pseudo potentials, because we use in these calculations pseudopotentials, which is described by this equation. And in our calculation, we used small core pseudopotential. So pseudopotentials. So it means that we have to treat explicitly 19 electrons for neutral molecule and 20 for anion molecule. So to do this, we used MolPro program package level and our new program spectroscopy. We used effective core potential, small small effective core potential created by Stoll. So it is pseudo potential from Cologne and Stuttgart group, and we used also basis set of Peterson and Puzzarini, but we had to optimize this basis set in order to reproduce proper values of electron affinities of silver atom and silver dimer. Because using original basis sets, it was not possible. So we used MRCI method, but especially the couple cluster method with singles, doubles, and perturbative triples with counterpulse correction, and we also checked mid bonds method, which was optimized at the experimental bond length, equilibrium bond length. Okay, to calculate vibrational levels and vibrational wave functions, we solve time-independent nuclear Schrödinger equation with this nuclear Hamiltonian, and we did this using our new code spectroscopy. And finally, I would like to show you our new results. So you can see here the ground states of the molecular silver anion, and the ground state of the silver dimer. And you can see here some discrepancies between the position of the minimum in two situations. These are our new results, and here you can see results which were used to explain experimental results reported by Anderson et al. So you can see that it is visible that these potentials are that model potentials are not so good in the comparison of our results, and it was surprised that when we look at the spectroscopic parameters and spectroscopy of the silver dimer and especially silver anion dimer, it was surprised that there is not so many data for these systems, and we think that our new results are now the best results which allow us to describe these two systems having potentials, having ground states potentials. So you can see, for example, that dissociation energy is very close to the experimental results, And also, as I said before, electron affinity of the silver dimer is very close to the experimental one, which was reported by Ho. Here you can see that for anion, silver anion dimer, there is less data than for neutral molecule. And we also see that we obtained very good results in the comparison with only one experimental data report by Ho. Here is also electron affinity of silver atom, and you can see that because it was one of our aims to create to reproduce this value. So we are very close to the experimental result. And finally, we was able to map row vibrational levels of both systems. And you can see some special regions on this figure. For example, this gray part corresponds to the part in which there is no decay possible. The green part is very important because in this part there is some vibrational levels, raw vibrational levels, which is inside the potential well of the some raw vibrational levels of the neutral molecule, which are inside the potential well of the silver anion dimer. And here you've got the very small part, red one, which corresponds to the part for which we can observe two possible paths of decays. So one is fragmentation, and another one is spontaneous electron emission. So the green part is connected with only with spontaneous electron emission, and the red part is in this red part, two channels of reaction are opened, and the blue part is connected only with fragmentation. So it is of course because of centrifugal barrier, which when the J is increasing, the centrifugal barrier is bigger and bigger. So you can see here that in this part we can observe. In this part we can observe fragmentation through the barrier. Analyzing this feature, we was able to find a critical J for which it is the last J for which the two channels are opened, and so spontaneous electron emission and fragmentation, and for J bigger than 1 from this critical J, only the fragmentation channel is opened. Okay, now I would like to say something about molecular quantum dynamics. We used time-dependent Schrödinger equation. It is also the standard approach with the wave packet, which is defined like this. And here you can see psi nodes Vj and psi Ej. These wave functions are eigenfunctions of the nuclear Hamiltonian, which I showed you before. And in our case, we choose two approaches. We in the first approach we have taken the Gaussian function which was placed on the effective potential curve. And in another approach, we just take the single vibrational eigenfunction to reproduce, to find the lifetimes and population decay from specific vibrational level. And we can define the time dependent population like this with autocorrelation function, and the Fourier transform of the autocorrelation function give us the spectrum, which I will show you later. So the goal is to solve the time-dependent Schrödinger equation. So we have to define the evolution operator. And in our case, in our approach, we used Kozlov method using Chebyshev polynomials. You've got here Chebyshev polynomials. And this is a very well-known approach, but it is, in our opinion, one of the best one, because for example, you can create expansion showed on this slide as long as you want. Of course, you have to have enough computational resources, but of course this is very high accuracy method, and that's why we used this method. This method is a part of JADE framework, which was created by Jan Kozicki, and I think very soon there will be another part of this framework which will be connected with quantum dynamics. So results. Here I show you lifetimes and level widths of the two selected vibrational levels, which we choose this levels because to show that when we are very close to the critical J, for critical J, two channels are open, and we would like to show how looks the vibrational predissociation in the for J a little bit larger than critical J. So we choose this J, and for V equal 155 and 154, we obtained time lives 57 picoseconds and 204 nanoseconds. And of course, we try to compare our results of the level widths with the level program calculated by level program, and the comparison is quite good. But in our opinion, the level widths of obtained by us are a little bit better because they were obtained by fully quantum mechanical approach. And you can see spectrum of the this J equal 254, and you can see several rotational several vibrational levels, and here you can see that the comparison of obtained by quantum dynamics approach and this one obtained by spectroscopy program, the comparison is very good, and we was able to show that vibrational predissociation dynamics is very fast in the comparison with the spontaneous emission. of the electron. To investigate the spontaneous emission of the electron, we have to calculate non-adiabatic couplings elements between initial and final vibrational states. But first of all, we have to calculate couplings between electronic states. And we did this. Jan Franz calculated this using his program Bumblebee. Sorry. And you can see some results of his calculations. So lambda Fi are non-adiabatic couplings between the ground states of the ground state of the between the ground states of the molecular anion and silver dimer with ejected electron. So you can see here the energy of the ejected electron, and the couplings looks like this. And these couplings are not so big. So why we tell about this kind of couplings that they are very weak couplings. And finally, we were able to show some results, selected results, which are connected with the probability of autodetachment of electron and autodetachment cross-section. And you can see that lifetimes of this is quite large. So it is seconds, and of course we observed that sometimes this process could have hours, because it is because of the weak couplings between these potentials. So this is rather small results which we was able to extract from all of combinations with combinations of vibrational and rotational quantum numbers. But anyway, we confirm by our calculations that what was reported in the Anderson paper, that this process is really long in the comparison of the predissociation. So we calculated, to summary, we calculated potentials. We obtained very high accuracy raw vibrational and electronic structure. We was able to map the raw vibrational levels of both systems and show regions in which two channels are opened, or only one channel is opened, and this channel where two channels are open is really small. Later we calculated dynamics of the raw vibrational predissociation, some lifetimes and level widths. We showed that this process is quite fast, nanosecond and picoseconds. And later we calculated non-adiabatic couplings to show the spontaneous, to calculate some features of spontaneous electron emissions. And this process is very long in the comparison of the dissociation. And we work on the codes which will allow us to calculate to do time-dependent quantum simulations with weak and strong couplings. Okay, so some acknowledgements, and thank you for your attention.
Thank you, Patrick. So we have some time for the questions or any comments, questions. Okay, I see Fernando, please.
Hello, Patrick.
Hello.
Oh, very nice talk. Very interesting. I have a question.
Yep.
Well, as you know, calculating the electronic structure of negative ions is a very complicated matter because these systems are extremely diffuse and large. And so I was wondering how good your description is at long distances of the electron of the electron that is, far away. Because, well, you showed the table in which you compare the I think was the electron affinities or the ionization potentials, and with but in order to calculate the vibrational and rotational structure, probably it's important to describe very well the region, the asymptotic region of the electron. And so I was wondering, with these the basis set you used, you mentioned it, but I didn't have time to look at it in detail. It was diffuse enough to describe this asymptotic region. So could you comment on this, please?
Yes, we hope yes, because we also because we not only optimized the original basis set of Peterson and Puzzarini, and also augmented this basis set using a lot of diffused elements. And also in the coupled cluster method, it is good to because it is good situation in the case of anion, because in the long region you've got two separate references. Yes, so because for molecular dimer, it is bad situation because we had to use multi-reference coupled cluster method, which is not so, there is not so many implementation of this method. But for anion, CCSD with the it's enough, and we also use counterpose correction. It was in our opinion very important. But yes, I think we did we added to our basis set enough diffuse functions and optimized carefully this basis set. It allows us to calculate really good electron affinity.
Okay, well, thank you.
Okay, more questions? I don't see any further questions or comments, so thanks again to Patrick and to all the speakers of this session. I think that we can close the session perfectly on time. And I remind you that there is the possibility to meet all the speakers on the discussion rooms. So all the corresponding links are available on the meeting webpage. And thanks to all of you, and see you tomorrow morning at 10. Bye-bye.